So here's some more applications of finding maxes and mins. This is still just optimization, so you can just think of this as part 2 of the optimization video. And we're just going to do examples. So some of these are a little more about kind of geometry. So for example, a 4-pen kennel of 640 square feet is to be constructed as shown. So we're going to build a rectangular pen with 4 kennels in it, and we're just using the picture to assume that all the kennels are the same size, because why wouldn't they be? So the total area of things has to be 640 square feet. So again, that's called a constraint. We need those things. And there's different costs associated with the different materials. It's $20 per foot for the sides, which are these things, and $5 per foot for the ends and dividers, which is these things. So in other words, we need 2 sides, right? And 1, 2, 3, 4, 5 ends and dividers. So what are the dimensions of the kennel that will minimize the cost? So it's always this kind of push and pull. Like, do we want a really long skinny kennel? Do we want a perfectly square kennel, right? Do we want a tall kennel? The answer is usually somewhere in the middle, but now because of the variable costs, there's no real way to just kind of guess. So, we do the math. So if you didn't have a picture, draw a picture and then just label stuff. So the tops and the bottom are what we're calling the sides. And then the ends are what I've just labeled as width. So, right, all the ends and dividers are length W, and both of the sides are length L, length width. So you can use different letters if you want, doesn't matter. All right, so our total cost is, 2 sides, so 2 times $20 times however many feet the sides are, plus 5, because there's 5 ends and dividers, times $5 times however many feet the ends and dividers are, right? So it's 2 times 20L plus 5 times 5W. That cleans up to just 40L plus 25W. So the problem we have right now is that that's not just a function of one variable. There's an L and a W in there. And like if we were to try and graph that, it's actually a 3-dimensional graph because there's 2 independent variables in it. So we need to write one in terms of the other. And notice the thing we haven't used yet. We haven't used that 640 square feet, so that's our constraint. That's how we relate L and W, so we can get one in terms of the other, so that we just have an equation in one variable, so we can do normal single variable calculus to it. So our restriction is that the total area of the thing is 640 square feet, so look at the picture, it's pretty simple. What does that mean? It means L times W has to be 640, right? So that's the area of that rectangle. So at this point, you have to solve that for one of the variables. And in this particular problem, it truly doesn't matter which one you pick. In some problems, it's like a lot harder to solve for one rather than the other. But this one, it's truly, the process is going to be exactly the same. So I picked W. No reason for that. So solving that for W is literally just you divide both sides by L, so W is 640 over L. And then we're going to stick that back into our original C, our function for C, and now the only variable in it is going to be L. Okay, so now this is truly a function. C, I could call it C of L. C of L equals 40L plus 25 times, we replace W with 640 over L. So we clean that up, and then we have our function that we're going to try to find the minimum of. 40L plus 16,000 over L. Okay, so again, that was the hard part. The setup generally for these is the hard part. You know what to do. In fact, one thing you could do right now is pause this video and just finish this problem by yourself. That's never a bad idea, right? If you get the same answer as me, you're good. Move on. Okay, so it's always good to write L, that over L is just L to the -1, because now we can just use the power rule on this thing. And to find the minimum value, we're setting the derivative equal to 0. C prime is 40 minus 16,000 L to the -2. set that guy equal to 0 and solve it. So as we're kind of seeing, it's good to actually switch back from that exponential notation when you have to solve for something, because it's more obvious what to do. So the algebra here is what I would do is I would just move the 16,000 over L squared to the other side, like that, and then multiply both sides by L squared. You can think about this as cross multiplying, so that then moves over with the 40. 40 L squared is 16,000, right? This is not a difficult equation. Divide both sides by 40. L squared is 400. And the solution to this equation is plus or minus 20. But in this case, as we've seen, one of those answers doesn't make any sense. You can't have negative 20 as a length. And that's fine. Just say that and be like, okay, throw it out. You wouldn't even have to write that. Just say, well, L is 20, because it obviously has to be positive. So it can be kind of hard to graph these things when they have big numbers, but it's easy on a computer. So I'm just going to say, okay, you can either use the graph or you can use the second derivative test, which is where you just take the second derivative. If that thing's positive at L equals 20, that means, think about what a positive second derivative means. That means that curve's concave up, like a upwards facing parabola, and that means that we have indeed found a minimum. So it's not a trick question. That is the min. So L equals 20 is the sweet spot. And then we usually want to get a little more information. If L is 20, you can just go back and use our equation for W in the first place. W is 640 over 20, which is 32. So if you think about it, my picture was bad. The ends are actually going to be longer than like the top, so they're going to be pretty tall, skinny kennels, right? But we didn't know that. We didn't know because of the variable cost of the sides and stuff. Right. So anytime we find what to do to achieve the minimum cost, I'm generally always going to ask you to tell me the minimum cost as well. So you just stick that back into the original equation. So this is just the y value of the graph. It's just 40 times 20 plus 16,000 over 20. So that's it. We're spending $1,600 on this thing. That's the least we can spend. Here's another thing. This is called an inventory cost model. So we have these production runs that we do periodically. And every time we do a production run, we crank out X items. Those X items go into inventory, so they kind of go into storage, and then they're taken out of inventory and they're essentially sold at a constant rate. So think about like if you took one out every day, like it's some sort of product that you just sell one of every day. So that's what we mean by removed from the inventory at a constant rate. It's helpful to look at this graph. Okay, so we have X units. So we start like the beginning of our month or whatever it is with the X units that we produced all in our warehouse. And then we take out, again, it could not be one per day. It could be one per minute. But we take them out at a constant rate. So that units in storage, that vertical axis just goes down at a regular rate until we're back down to 0. And then we fill it back up again, right? Because we did another production run. So this is instructive because we have to know the average units in storage. Now, to do the average value of a function is actually a calculus thing that we don't know yet. But if you look at that graph, you can kind of see that the average value of that function, it should just be right in the middle, right? It should be because it's just clipping down like that. This is called like a sawtooth kind of function. So the average value of that, you might just have to take my word for it, is just right in the middle there, which is x over 2. So that's going to come up in the equation. That's the average number of units that we have in storage at any one time. And then again, it's because they're being removed at a constant rate. If they weren't and it was being varying, we'd have to do something called an integral, which you'll get soon. Okay, so it costs money to produce each unit and it costs money to store each unit. But if we lower one, the other one can go up and vice versa. So they're obviously tied in with each other. So it's the same kind of thing. You see how it's kind of like the last problem? If we make it longer, we have to, the width gets smaller and vice versa. So there's some sweet spot in the middle where in this case we're going to obviously minimize our total costs. So we have production costs and storage costs. We want to minimize them, but they are related. Example. A company needs 60,000 items during the whole year, and preparation for each production run costs $800. So that's not even to produce the item, that's just a flat fee we have to pay to prepare for our production run. So whether that's paying your employees or costs so much to run the factory or whatever. So to produce one item costs $8, and to store an item for the full year costs $1.50. So everything that's sitting in storage is costing you $1.50 per year. So we want to know a couple things. Well, the main thing is find the number of items that should be produced in each production run. So if you go back up to the top there, that's what I called X. We produce X items each time in order to minimize the cost. So in other words, should we do a production run every month? Should we do 12 total production runs? If we did, we would need, we need 60,000 items total. So we did go 60,000 divided by 12. That's how many items we would then have to produce in each production run. Oh, the other assumption here is that we produce exactly the same amount of items every time, or else the graph wouldn't look like that, right? So we always produce X items in each run, right? So do we do a production run every day? Do we do a lot of production runs and only make a little bit each time? Or do we do just like 1 or 2 big production runs and make them all, right? Obviously, no. There's something in the middle that's going to be the sweet spot that minimizes the cost. Okay, so we got to put some stuff together here. Again, this is the tricky part. All right, so we're producing X items every run, but we need a total of 60,000 items. And remember, each production run, we produce the same amount of stuff. So, like, if we produce 10,000 things every run, we only have to do 6 of them. See what I'm saying? If we produce 60 things each run, we'll have to do 1,000 of them to get our quota. So we need 60,000 items for the total year. So how am I getting those numbers? I'm dividing. So every year we have to do that many production runs, whatever 60,000 divided by whatever X turns out to be. So here's our formulation of our costs. The total costs just for production are going to be the number of runs we do times however much it costs to do a run. That's $800. We know that. We were given that. Plus the number of items we make in one total times the cost it takes us to make one item. So that's $8. We were also given that. All right. So we already established we're doing 60,000 over X production runs times, we're given it costs us $800 to fire up our factory or whatever every time, and then plus the number of items we need total, we're given that it was 60,000 times 8. So it's like we're spending that no matter what we're spending 60,000 times 8. The other term depends on like how many runs we do, right? The more runs we do, the less that's going to be, or the more that's going to be, right? All right, so that simplifies to 48 million over X plus 480,000, so big numbers. So that's just for production costs. Now we need to figure out our storage costs. So the total storage cost, so that's where we need that average. On average, we're always going to have X over 2 things in storage, on average. So we just take that average and we multiply it by how much it costs to store one item for the year. So we have those as well. So there's an average of X over 2 things in storage at all time. Refer to that graph. And we were given that it costs $1.50 for the whole year to store each item. Well, that's not much. So that simplifies. Half of 1.5 is 3/4. So that's just 3/4 X. Okay, so finally our total costs for production and storage are we just get that by adding those 2 things together. The total costs are finally our function for production and storage are C of x. I can write it like that now because it is just a function of a single variable x. X, remember, is the number of items we produce in a run. So C of x is 48 million over x plus 480,000 plus 3/4 x. Okay, hard part's over. Again, now would be a good time just to pause this video and just do this yourself, right? You know how to do this next part. Just set C prime equal to 0. So, right, why wait for me? You should be able to do it. Go, pause it, do it. Okay, I'm moving on. So C prime is just, so I kind of skipped a step. So you'd write 48 million over x is 48 million x to the negative 1. So the derivative of that first term is negative 48 million x to the negative 2. The 480,000 went away. That was just a constant. And the derivative of 3/4 x is just 3/4. And we're seeing where, if anywhere, that equals 0. So algebra-wise, again, I'd probably just move one of the terms to the other side, and I'd do that in a way that both sides are positive, like that. And then I also switched the x to the negative 2 back to an over x squared, because that's easier to deal with in terms of solving equations. Okay, so 48 million over x squared equals 3/4. And then I guess you could cross multiply. 3x squared equals that times 4 is 192 million. Divide by 3. X squared is 64 million. Square root both sides of that thing. X is 8,000. So 8,000 squared is 64 million. Okay, so that's a nice clean number. And when you get a nice clean number, you kind of think, hey, I probably did it right because they probably set it up that way, right? If you got some weird decimal, it's like, that doesn't seem right. But if you get a super even number like that, chances are whoever made up the problem meant it to be that way. So yay, we're happy. So that was the number of items we're going to do in each production run. So let's just get a little bit more information. Right, again, that is a minimum. You'll have to use a graph or take the second derivative and see if it's positive or negative there. It could be a max, right? Like, if I could mess with you and give you one where, oops, you just found the maximum cost. Or you could get two answers and one of them is a maximum cost and one of them is a minimum cost. Chances are there is no maximum cost because you could probably just keep getting worse and worse and worse and it would like go to infinity. But who cares? We don't want that. So the actual minimum cost, again, you just stick it back into C. So it's 48 million over 8,000 plus 480,000 plus 3/4 times 8,000. And that's obviously just a calculator thing. $492,000. So that's the least we can possibly spend on our whole year of producing and storing things. Just for giggles, let's find out how many runs we'd be doing every year. So remember that's the number that was just 60,000 divided by x. We need a total of 60,000 things. And now we know that we're producing 8,000 units every time we do a run. So 60,000 over 8,000 is 7.5, which might seem weird that you would get a fraction there, but not really. Your runs wouldn't have to just end on December 31st. Right? We're doing it in the way that's most optimal. So if you just divide 12 by that number, you see that it's every 1.6 months. So a run lasts like a little more than a month and a half in our ideal situation.